Hey there, it's Shannon Matchick-Myers, and today we are checking out linear equations and differential equations. So this is really awesome. You basically kind of like getting a common denominator with, rational expressions when you're trying to add them or subtract them. This is sort of similar in the sense that we make the expression look really complicated. But it ends up making the differential equation much easier to solve. Not always easy, but solvable. All right, so let's fasten our seatbelts and check this out. So definition 2.3.1, linear equation. A first order differential equation of the form a sub 1 at x times dy dx plus a sub 0 at x times y is equal to sum g at x is said to be a linear equation in the variable y. So here we go. Standard form. Consider dividing both sides of the linear equation by a sub 1 at x, which is the lead coefficient. So we'll rewrite that equation, a sub 1 at x times dy dx plus a sub 0 at x times y equals g at x. Now, if we divide through by a sub 1 at x, then what happens is we get dy dx isolated. Now we get two functions in terms of x as a fraction, right? So, or as a ratio. So we rename this as capital P at x, and that's times y. And again, renaming g of x divided by a sub 1 at x to f at x. Cool? So, just so we're good to go here, this ratio was renamed p at x, and this ratio over here was renamed f at x. Cool? All right. So, at the end of the day, this here is the equation we'll be working with. So I'll rewrite it. Dy dx plus p at x times y equals f at x. Groovy? All right. So standard form is this guy here. All right, so the first example, determine if the given differential equations are separable. Well, one way to do this is just to try to separate them, right? So multiplying both sides by dx, we would get dy is equal to sine at x times cosine at x dx. And yes, they're totally separable because the factors to the dx term are functions of x, and the factor to the dy term would just be a 1, right? Which we can integrate with respect to y. So yes, this one is separable. What about this next one? Okay, well, dy dx minus y equals x. So if I isolate dy dx by adding y to both sides, I'll get this. And then if I multiply both sides by dx, I'll get dy equals the whole quantity x plus y times dx. So there's no way we're going to be able to get that y as a factor to dy without having dx there. So this one, we would say no. But the good news is that's linear in form, and so we're going to learn how to do stuff like that. Aren't you excited? I am. All right. So, method of solution. The method for solving this linear differential equation, dy dx plus p at x times y equals f at x, DE's differential equations, hinges on the fact that the left-hand side of the equation can be recast into the form of the exact derivative of a product. So we're using ideas of differentials by multiplying both sides by this special function, call it mu at x. Let's check it out. So here we go. If we take a look at this mu at x, we don't know what it is yet, okay? And mu at x, it's some function in terms of x times dy dx, right? Is equivalent to, if I rewrite this a little bit, because y is a function of x as well, right? So this would also be equivalent to the derivative with respect to x of this product of mu times y. Both are functions of x. Well, what are we going to get here? Using the product rule, we would have mu times dy dx plus du dx times y. Groovy? Which is mu dy dx plus mu times p times y. Cool, cool? Okay, now using separation of variables, all right, basically, whoops. So keep that on your back burner for just a moment. Now, taking a look over here. Now we're going to look at the left-hand side of the standard form of the equation. This guy here, just the left-hand side. So this one has dy dx plus p at x times y. Groovy? So that's the left-hand side of the standard form of the linear equation. So now if I look at this and I multiply this one by mu at x, then I will get mu, just writing it as mu instead of in function notation, times dy dx plus mu times p. So notice that these two match. Cool, cool? So the derivative with respect to x of mu times y is equivalent to multiplying mu at x into the left-hand side of the standard form of the linear equation. So, in order for this to be true, right, what has to be the case? Beautiful. Du dx has to equal to what? Mu, actually this is d mu dx, mu times p, right? So du dx has to equal to mu times p. So, simplifying this guy, we're going to have du is equal to mu times p dx, and then dividing by mu, you'll have d mu over mu is equal to p times dx, and then we set up a separate, their variables are separated, and so we'll get natural log absolute mu is equal to the integral of p at x dx plus some constant 1. Don't worry, you don't have to memorize all this. It's easier just to, I'll show you the method soon. Now, and actually to be totally proper, let's do this. Natural log absolute mu at x. So now, what are we going to have? Well, if we write this in exponential form, then we will have mu at x is equal to e raised to the integral of p at x dx plus some c1. Well, this is equivalent to e to the integral p at x dx times e to the c1. Renaming e to the c1 as some constant, we'd have mu at x, and I took off the absolute value bars because it's equal to an exponential, so it'll be that can never be negative. So then we'll get some c2 times e to the integral p at x dx, and that c2 just comes from here. E to the c1 is another constant. And hey, why don't we just let c2 equal to 1? Why not? So, at the end of the day, mu at x is equal to e to the integral p at x dx. Cool, cool? So, this is what we're taking away from this. We have our integrating factor is this. So, let's take a look at what the heck we do with all this, all right? So now, if I now, start working with this, we have the whole equation dy dx plus p at x times y equals f at x. And what's happening is we are multiplying through by our mu at x. But what is mu at x? Mu at x is e to the integral p at x dx. Okay, so now for a little bit of magic. All right, would you agree that we could rewrite p at x as the derivative with respect to x of the integral of p at x with respect to x? Cool? So let's look at this left-hand side. We're going to write this as d dx of e to the integral p at x dy, nope, dx, times y plus d dx of the integral p at x dx times e to the integral p at x dx. So we have the derivative of what's inside the power of that e, right? And then we still have the y hanging out. So now what ends up happening here, and that of course is equal to the other side, e to the integral p at x dx times f at x. But the beauty of this is that this is using the product rule, right? And so here what we're doing is we're saying, oh, this is going to be the first e to the integral p at x dx times the derivative of the second, right, dy dx, plus the derivative of the first, which is d dx of integral p at x dx times e to the integral p at x dx times y, not equals plus, which is just the product rule. So then we write it how it would look before applying the product rule, and we'll just get d dx of the first, which was e to the integral times p at x dx times the second, which is y. Isn't that cool? And that's equal to e to the integral p at x dx times f at x. Now, solving for y, we're going to end up having separating these equations, and then, so sorry, it looks like we're going to have to go to another page. I thought I had enough room. So here's where we were. All right, so now what's going to happen is we'll separate those variables. So multiplying both sides by dx, we'll have e to the integral p at x dx dy is equal to e to the integral p at x dx times f at x times dx. And then integrating both sides. On the left side, it looks complicated, but it's being integrated with respect to y. So we will have y times e to the integral p at x dx is equal to the integral of e to the integral p at x dx times f at x dx plus some constant. So isolating y, we'll have e to the negative integral p at x dx. That's just using law of exponents, dividing both sides by e to the p at x dx, and then writing it in the numerator, times the integral of e to the integral p at x dx times f at x plus c e to the negative integral p at x dx. Cool, cool? And so this is the one that we're going to utilize here. But again, I don't want you to memorize this. What you want to memorize is the format, so you can find your p of x, find your f of x, and then also remember that integrating factor. Cool? All right, so let's scope it out, what we got to do here. Solving a linear first order equation. Remember to put a linear equation into standard form. Just a reminder, standard form was dy dx plus p at x times y equals f at x. From the standard form, identify p at x and then find the integrating factor e to the integral p at x dx. You do not need a constant when evaluating the integral of p at x dx. Multiply both sides of the standard form equation by the integrating factor. The left-hand side should automatically, if you did this right, be the derivative of the product of the integrating factor e to the integral p at x dx and y. So you have d dx of that integrating factor e to the integral p at x dx times y equals e to the integral p at x dx times f at x. Then you integrate both sides of the last equation, the one we just wrote, and we solve for y. Now here's a note. If the term with the constant approaches 0 as x approaches infinity, it is called a transient term. All right, let's do an example. Check it on out. So please find the general form of the given differential equation. Give the largest interval over which the general solution is defined. Determine whether there are any transient terms in the general solution. So let's just make a little, write down what we know and go from there. So first of all, we definitely want to isolate, well, not isolate dy dx, but we want a coefficient of 1 in front of the dy dx. So if we multiply or divide everything through by 3, we're going to get dy dx plus 4y equals 4/3. Cool so far? All right, so now let's make our little list. f at x is just 4/3. It's on that right-hand side of the equal sign once we got dy dx to have a coefficient of 1. P at x is equal to 4. It's the coefficient to the y term. So our integrating factor e to the integral of 4 with respect to x, and that is just e to the 4x, correct? Oh, right, beautiful. Now we multiply it in. So we multiply both sides by our integrating factor, which was e raised to the 4x. And then we will have e to the 4x dy dx plus e to the 4x times 4y equals 4/3 e to the 4x. Cool, cool? Now, the way that we formatted this is that the derivative with respect to x of e to the 4x times y is equal to the left-hand side above, and then that in turn is going to be equal to 4/3 e to the 4x. Groovy? And so think about it, right? First times derivative of the second. So the first has to be e to the 4x. The second has to be y. And the derivative of e to the 4x is 4e to the 4x. Pretty groovy, huh? All right, so now separating the variables somewhat, we'll have e to the 4x times y, times dy is equal to 4/3 e to the 4x, and then integrating both sides, and then we also had our dx here, we will end up with e to the 4x times y on the left side is equal to 4/3 times e to the 4x divided by 4, integrating that exponential term, plus some constant, now I want to isolate y. So y would equal to e to the negative 4x. The 4's divide out, right? So this will be just times e to the 4x divided by 3. Don't forget to bring that e to the negative 4x to the constant term as well. Well, the exponential terms will the exponent will zero out, so there'll be 1. So we end up just getting 1/3 plus ce to the negative 4x. Isn't that amazing? Now, let's identify as looking for that transient term, right? So remember, if the term with the constant approaches 0, as x approaches infinity, it's called transient. So as x approaches infinity, this will indeed zero out, the ce to the negative 4x, because of the negative in the exponent. So let's do this. Ce to the negative 4x is a transient term. We also needed to figure out the domain. So the domain we figure out from our f of x and our p of x. So do you see there's no restrictions on our domain? So minus infinity, less than x, less than infinity. And we'll put that in there, and then we'll box everything. Groovy? All right, so now let's take a look at part B. Part B, we have the same direction. So I'm going to rewrite y prime as dy dx, and then we have plus 2x, that quantity, times y. I'm grouping it so we can see whatever our p of x is, and that's equal to x cubed. So when we're making our list, we have f at x is equal to x cubed, p at x is equal to what? Awesome, 2 times x. We don't have any limitations on the x for the domain, so minus infinity, less than x, less than infinity. And our integrating factor will be e to the integral 2x dx, which, when we integrate that, we would get what? Beautiful, e to the x squared. And then multiplying both sides by our integrating factor and trucking along. So remember that this is going to give us the derivative with respect to x of these terms. E to the x squared would be the first factor, y would be the second factor. And then that's going to equal to e to the x squared times x squared. And then we'll have e to the x squared dy is equal to, I'll write it as x squared e to the x squared dx times x cubed. And so this will be my dy, I have my e to the x squared in front, is equal to x cubed e to the x squared dx. Now, in order to integrate that right-hand side, I'm going to have to use, drum roll please, integration by parts. So, using our IBP, integration by parts, we're going to let u equal to x squared. Du will be equal to 2x dx. dv is going to be x e to the x squared. That's setting up that integration. We will need to have a 2, I'll just do it as 2 over 2. We will have v is equal to 1/2 e to the x squared. So what did we find? We found the integral of x cubed e to the x squared with respect to x equals u times v. So x squared over 2 times e to the x squared minus the integral of e to the x squared 2x dx, which sets us up nicely for that integration. So we get x squared over 2 e to the x squared minus 1/2 e to the x squared. Cool, cool? All right, so this one will be, I'll write that on our right side, plus our constant of integration. That was after integrating. And then when we integrate the left side, we're just going to get y and then times our e to the x squared times y. So then, isolating y, we're going to multiply e to the negative x squared through these. So times x squared over 2e to the positive x squared minus e to the negative x squared times 1/2 times e to the x squared, and then plus c e to the negative x squared. All right, so now let's clean it up. The e to the x squareds, multiplying them through become 1. So we'll have x squared over 2. And then again, the negative x squared plus x squared, when you combine the exponents, is 0. So the exponential function becomes 1. So we'll have minus 1/2 plus c e to the negative x squared. Cool? And we're all done. All right, on to the next. Part C. Cosine squared at x times sine at x dy dx plus cosine cubed at x times y equals 1. So here we go. We need to divide each term by cosine squared at x times sine x. And then we'll multiply by 1 over cosine squared at x times sine at x. Groovy? So we'll have dy dx plus cotangent at x, that quantity times y, is equal to secant squared at x times cosecant at x. Cool? So f at x is secant squared at x times cosecant at x. P at x is equal to cotangent at x. And so our integrating factor will be e to the integral cotangent at x with respect to x, which will be equal to e to the natural log absolute sine at x. Now let's look at our domain. If you look at the overlapping domain here, we've got the secant function, the cosecant function, and the cotangent function. So we're going to be from 0 to pi over 2 non-inclusive for the overlap there. And then that means that we can take the absolute value bars off over here. And then when you evaluate an exponential at the natural exponential at the natural log, you just get what's inside there, which is sine at x. So much easier, isn't it? Woohoo! Nice. So then, multiplying both sides by that integrating factor, sine at x, we will have sine at x times dy dx plus sine at x times cotangent at x, which is cosine at x over sine at x, times y. That's all going to be secant squared at x. Well, the cosecant at x times sine at x is just 1. they're reciprocal functions. So then, cleaning this up, let's see what happens. We will have d dx of sine at x times y is equal to secant squared at x, and then getting it ready to integrate, separating the variables, we'll have sine at x dy is equal to secant squared at x dx. And integrating, let's see what we get. We will have y times sine at x is equal to tangent at x plus c. So y equals to, I'll write the tangent as sine at x over cosine at x. We're going to be dividing by sine at x, so multiplying by 1 over sine at x, plus c times 1 over sine at x. So we will get y equals, these sine at x's cancel, we'll have secant at x plus our constant times cosecant at x. Beautiful. And then, of course, we have to decide if it's transient. It is not. As x approaches infinity, the cosecant function does not approach 0. So no transient term. I might have forgot to do that on the last one. No transient term, and then we found out that it goes 0 less than x less than pi over 2. And we're all done. Let's double check if we identified transient terms here. We did not. This one here is going to be a transient term, right? So ce to the negative x squared is a transient term. And what did we say? Our interval was minus infinity, less than x, less than infinity. Groovy? All right, I think it is. Okay, example 3. Now we're given an initial value problem. So let's go for this. We also want to give the largest interval over which the solution is defined. So, same deal, okay? We're just going to isolate dx dy this time. And then it's going to be a little bit different. Oops. It's going to be a little bit different. So I'm going to get the divide through by y. So this will be minus x over y is equal to 2y squared divided by y. Cool, cool? All right. So now we'll have dx dy minus x over y. And actually, let's write this a little differently. Now we're going to be looking at f of y and p of y because the dx was in the numerator there. So we want 1 over y times x. So this will be our p of y. And then that's going to equal to 2y. So we now have f of y is 2y. P of y is 1 over y. And I'm sorry, we also have this negative, so I can write that as plus a negative. Make that negative. So our integrating factor is going to be e to the integral of negative 1 over y dy. Now let's figure out our interval for y. So y can't be 0, correct? And y is also, for what we're looking at with our initial condition, y at 1 is 5. So we're going to go on we need it to be on the positive end. So 0 less than y less than infinity. So here we go. When we integrate this, we will get e to the negative natural log absolute y. But we said y was positive, correct? So this would be e to the natural log y to the negative 1 because of the negative multiplied to the natural log. And then this in turn is just going to be y to the negative 1 or 1 over y. Pretty cool, huh? So multiplying through by 1 over y, we will have 1 over y dx dy minus 1 over y squared times x equals 2. So, and sorry, I put a dx, not a dy. And so d dy this time of 1 over y times x equal to 2. So we have 1 over y dx is equal to 2 dy, multiplying both sides by dy, and then integrating with respect to x on the left and y on the right is going to give us x over y equals 2y plus c. And then x will be 2y squared plus c times y. Now let's apply our initial condition, right? Because we have that wonderful initial condition. So y at 1 is 5. So I put in a 1 where I see an x and a 5 where I see y values. That's the kind of tricky part here. And then we'll have 1 is equal to 50 plus 5 times c. So 49, negative 49 fifths equals c. So then back substituting what we found, we will have x equals 2y squared minus 49/5 times y, where there's no transient. Oh, we don't need to worry about a transient term here because we found c, but we do know that y is between 0 and infinity. Groovy? All right, perfect. All right, part B, another intermediate value problem. So dy dx plus 4xy equals x cubed e to the x squared. So it's already set up for us to find our information. F at x equals x cubed e to the x squared. P at x equals 4x. Our integrating factor will be e to the integral 4x dx, which is, if you integrate 4x dx, you'll have e to the 2x squared. Cool, cool? All right, so here we go. We need to multiply both sides by our integrating factor, which is e to the x squared. And then that will give us, e to the 2x squared. And that will give us d dx of e to the 2x squared times y. On the right side, we will have x cubed times e to the x squared plus 2x squared. So we'll have d dx of e to the 2x squared times y equals x cubed times e to the 3x squared, adding those exponents. All right, so let's do this thing. Now we'll be looking at e to the 2x squared dy is equal to x cubed e to the 3x squared dx. All right, integration by parts, woohoo! So here we go. I'm going to let u equal to x squared. So my du will be 2x dx. dv will be equal to x e to the 3x squared dx. And then integrating both sides, I need a 6 here. So I'll divide by 6. And then when I integrate both sides, I will have v is equal to 1/6 e to the 3x squared. Groovy? All right. So now, putting it together, the integration by parts, the integral of x cubed e to the 3x squared with respect to x equals u times v will give us x squared over 6 e to the 3x squared minus 1/6 integral v is e to the 3x squared du was 2x dx. Cool so far? Now I need a 6x there. I have a factor of 2, so if I multiply by 3, I'll have what I need for my derivative, and then I'd have to go times 1/3. So then this will equal to x squared over 6 e to the 3x squared minus 1/18 e to the 3x squared plus our constant. So writing that into the right-hand side, we'll have 1/6 x squared e to the 3x squared minus 1/18 e to the 3x squared plus our constant. After integration. And on the left-hand side, we'll have e to the 2x squared times y. Isolating y, we will have e to the 2x squared times 1/6 x squared e to the 3x squared. And then actually it's an e to the negative 2x squared minus 1/18 e to the 3x squared plus c. So I will have 1/6 e to the, x squared, e to the 1x squared when I combine those, minus 1/18 e to the 1x squared, and then plus c e to the negative 2x squared. Applying our initial condition now. Our initial condition was y at 0 is -1. So, in for y, I'll put -1 equals 1/6 0 squared e to the 0 squared minus 1/18 e to the 0 squared plus c e to the negative 2 times 0 squared. And this is where I plugged all that good stuff in. So we'll have -1 is equal to, this term zeroes out, minus 1/18, that'll be 1, and then plus c times 1. So that means when I add 1/18 to -18/18, I'll have negative 17/18 is equal to c. And then rewriting, so back substituting, we'll have y equals 1/6 x squared e to the x squared minus 1/18 e to the x squared minus 17/18 e to the negative 2x squared. And then let's see our interval here. So our interval for our solution, we had a negative output for y, and let's see, but our x's can be any real number. There's no condition on there. So this will be our interval. And there's no transient term, but there wouldn't be with an initial value problem. So we'll just put our interval, and we're good to go. So I know it's kind of a long process, but you gotta admit it's kind of cool, isn't it? All right, piecewise linear differential equation. In the construction of mathematical models, it can happen that one or more coefficients in a differential equation is piecewise defined, is a piecewise defined function. So the evil plan is to solve the initial value problem in two parts, corresponding to the two intervals over which f at x is defined. And then you piece the two solutions together so that y at x is continuous. So let's take a look at this guy here. So first, we'll have, I'll just do it like an a and a b, dy dx. This is plus 1 times y, and I'll just do that first interval 1. We're already given that interval of solution, and so now we have our f of x for, you know, our setup for our integrating factor is just 1. Our p at x is also 1. And so our integrating factor is going to be e to the integral of 1 dx, which is e to the x. Cool, cool? All right. And then multiplying through by our integrating factor, we'll have e to the x dy dx plus y e to the x is equal to e to the x. And then as we've been examining, we'll get d dx of e to the x times y, and that's going to equal to e to the x. And then setting it up for integration, we'll have e to the x dy is equal to e to the x dx. So, integrating, we will have e to the x times y is equal to e to the x plus c. Isolating y, we'll get e to the negative x times e to the x plus e to the negative x times c. So y will equal to 1 plus c e to the negative x. Cool, cool? Now, applying our initial condition to this one, because it's in that interval, we'd have y at 0 is 1. So when we plug it in, we'll have 1 equals 1 plus c e to the negative 0. And that in turn will give us one minus 1 is 0, so we'll get 0 is equal to c times 1, which is just 1. So c is 0. And so for our first one, we're going to end up with, so this is back substituting, we'll have y equals 1. Cool, cool? All right, now we'll go and do the other side. So we'll call this b. So now we're doing dy dx plus 1 times y equals negative 1. So our f at x is negative 1, p at x is 1. Our integrating factor will be the same as last time. E to the integral 1 dx equals e to the x. And multiplying both sides by e to the x, our integrating factor, we'll have e to the x dy dx plus e to the x times y equals negative e to the x. So then we have d dx of e to the x times y equals negative e to the x, and then e to the x dy is equal to negative e to the x dx. Integrating both sides, we shall have e to the x times y equals negative e to the x plus c, and y will equal to e to the x times negative e to the negative x, times negative e to the x plus e to the negative x times c. And then this will be y equals negative 1 plus c e to the negative x. Now, to figure out this one, and let's call this C2. C2. So now, to figure this one out, we have to use the first one we could use the initial condition, right, because it was within that interval. But for this one, we have to think of it some other way. So to find that second constant, what we're going to do is this. We're going to set, they both have to, in order for this solution to be continuous, right, there can't be a jump discontinuity or a break, right, at x equal 1. So here I'm going to plug in 1 for my x's. So negative 1 plus c2 e to the negative 1 is going to equal to 1, right? So that I have that continuity here. So now we'll have negative 1 plus c2e, oh actually, sorry, I can do more there. I'll have c2e to the negative 1 is equal to 2. So isolating c2, I'll have 2e to the positive 1. So c2 is just going to be 2e. So solving for my function at the end of the day, we're going to have y equals one for that first one, and that's when 0 less than or equal to x less than or equal to 1. And then let's go back substitute. I didn't do that. So back substituting, if c2 is 2e, then I'll have y is negative 1 plus 2e e times e to the negative x. Combining those exponentials, I'll have negative 1 plus 2e to the 1 minus x. So that's what I will get here. Negative 1 plus 2e to the 1 minus x, and that's for x greater than 1. Cool, cool? And that's the final result for that problem. All right, now the error function. In math, science, and engineering, some important functions are defined in terms of non-elementary functions. So we saw that with that sign at x squared, or non-elementary integrals, Two such functions are the error function and the complementary error function. So the error function is denoted ERF at x, and it happens to equal, I'm not going to go into y, but it happens to equal 2 over the square root of pi times the definite integral from 0 to x e to the negative t squared with respect to t, and the complementary error function is denoted ERFC at x, and it's going to equal to 2 over square root of pi integral from x to infinity, so it's an improper integral, of e to the negative t squared dt. Cool, cool? Now, if you divide both sides of these equations so using the known result that the integral from 0 to infinity of e to the negative t squared dt happens to be equal to root pi over 2. If you divide both sides by root pi over 2, you would have 2 over root pi is equal to, because one side here would be 1, right? Times the integral from 0 to infinity of e to the negative t squared dt, and that would equal to 1. So now what we want to do is break this integral up. Remember that you can break integrals up somewhere, in the center that's defined. So if we look at the whole thing, 2 over root pi times the integral from 0 to infinity of e to the negative t squared, that's going to be equivalent to the integral from 2 over root pi times the integral of 0 to some x of e to the negative t squared dt plus 2 over root pi times the integral from x to infinity of e to the negative t squared dt, which has to equal to 1 because they're complementary. And so this here is the error function of x, and this guy here is the complementary error function of x. Groovy? And as we see, when you sum them, you get 1 because of the property of them being complements. So when would we use this? Well, when we're solving an initial value problem and see that indefinite integration of the right-hand side of, remember we have d dx on that left side, you have your e to the integral p at x dx times y on that left-hand side. But on the right-hand side, if you get something that's a non-elementary integral, when you have this stuff here, this is where you would use it. You would use it over here with this one. If that would lead to some non-elementary integral, then it's convenient to use definite integrals integration instead over the interval from x sub 0 to x. So let's look at this next example. Sorry, it was partially on that page. We've got x squared dy dx minus y equals x cubed. Y at 1 is 0. So rewriting, we'll have dy dx minus y over x. Actually, I'll write it like this. Nope. One over x cubed times y. That gives me my one over x squared is my p of x. Well, actually, negative 1 over x squared will be my p of x. And then that equals x cubed. But I also have to divide that one by x squared. So that leaves me with dy dx plus negative 1 over x squared times y is equal to x. So going through our little procedure, we have f of x is x, p at x is negative 1 over x squared. So y at 1 is 0. And so basically, we would end up having, we'll go from 0 non-inclusive to infinity for our x. I guess you could do negative infinity to 0 if you wanted, since y had a 0 result. Or negative infinity, yeah, negative infinity to 0, but I'll just do this one. The integrating factor would be e to the integral negative 1 over x squared dx which is equal to e to the integral 1 over x dx. Which is equal to e to the 1 over x. Okay, so now coming back over here, multiplying both sides by e to the 1 over x, we'll have our d dx of e to the 1 over x times y on the left side is equal to xe to the 1 over x. So we would have e to the 1 over x dy is equal to xe to the 1 over x dx. Well, integration by parts is not going to work on this one, right? Because you've got the 1 over x. So if you had x instead of 1 over x, it would have been fine. But we don't. And so on this one, we can go ahead and we can take a look at this and we can say we're going to integrate, right? So this will be e to the 1 over x times y equals. Now on this other side of it, we're going to make this into a definite integral, okay? So this is going to be the integral from 1 to x. I'm choosing 1 because 0 isn't defined, all right? And I'm going to put my dummy variable t in here. And then we'll have plus our constant of integration. And then putting in our initial condition here. What was that again? Y at 1 is 0. So that means that we'll put in a 1 for x, 0 for y, the integral from 1 to 1 of te to the 1 over t dt, and then plus c. Well, when you don't have a change of x, the whole integral zeroes out. So that's 0. And then the left-hand side is 0. So we end up with 0 equals c. So, back substituting, we'll have e to the 1 over x times y equals the integral from 1 to x of t e to the 1 over t dt plus c, multiplying through by e to the negative 1 over x, right? We'll end up with, oh, sorry, but our c was 0, right? So we're putting in 0 for c. So we're doing with c equal to 0. We'll end up with y equals e to the negative 1 over x times the integral from 1 to x of t e to the 1 over t dt. All right, and we're good to go. And you know what? That wraps it up for today. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, hit like and please subscribe. Bye.